everybody. I hope everyone's having a wonderful day. So, anyways, we're going to be picking up from where we left off last day. So last day we had talked about heaps. Now, one thing I didn't really tell you is where the name heap where it makes the most sense. So if you look at our heap over here, now remember a heap is a binary tree where what we do is we maintain two properties. We maintain the heap order property. That is where if I give you any key, its children must be at least the same size as, it's at least this or bigger. So for example, in 6, you'll notice there's 2 children are 7 and 10. It's okay if it was 6 here. However, if this was a 4, this would violate the heap order property because now all of a sudden this would be smaller than its parent. So does everybody see that? So if I give you any one node, it must be either equal or greater than its parent. Now, the name heap, you can imagine this like a pile. It looks kind of like a big pile. So I grab things off the top of the heap. So that's where the name heap, it makes the most sense. This is not to be confused with things like heap memory, where we talk about the heap, as in this kind of space where we allocate things like arrays and all these other things into the memory. That's not what I'm referring to. I'm referring to like a pile. Think of a pile. So first, I apologize if you hear a cricket by any odd chance. I've been trying to hunt it down. For some reason, I just can't seem to locate it. It might be hiding in the walls. I don't know. The point is that hopefully it adds a little to the mood if you can hear it. If not, that's okay too. So last day I told you that we're going to be implementing a heap using an array. So the array, and we can index each of the positions in the array such that if the root is going to be sitting at position 0, any left child will be 2 times whatever the position is for your node at a given spot. So for example, the left child of the root is 6. It's located in position 1 because we can multiply that position by 2 and we can add 1 to it. Likewise, the right child, it's whatever the position is in the array times 2 plus 2. So you can do this to look at the entire array. Note that there's also a way you can compute the parent, as I mentioned last day. And the whole idea here is we want to maintain the two following properties. You can think of these as invariants, things that we always want to maintain as we go along so that we always get the nice properties we're looking for. That's going to be one of the big strategies in this course for a lot of the later data structures we're going to talk about, including this one, is that we're going to maintain those 2 properties so that we can ensure that the height is what? It's big O of log n. Last day we've proven that if it has these 2 properties, this binary tree will have height log base 2 of n, rounded down. Okay, let's talk about how we're actually going to do things with our heap. So first, let's talk about inserting. You're going to find a lot of these algorithms, they're going to take very natural structure. It's going to use the properties that we have. So what I'm going to do is I'm going to store my element as a new node. Now remember, the node part is thinking about the tree itself. Its representation, you'd be storing it in a location in the array. New node in the heap. I mean, if you really want to take this literally, you could quite literally implement this as a linked, you can use the link tree implementation I gave you. I'll give you a more specialized version when we start talking about other types of trees. So you can implement this as a literal tree in terms of data structures, but it's not as easy as implementing it with an array like this. Meaning I'm going to increment the number of elements. It will be placed on the deepest level but furthest possible to the left. Furthest possible to the left. So let me just first do that. So what I'm going to do is I'm going to perform an insertion on this tree. tree here. So I'm going to have my heap. I'm going to insert it in. So imagine I insert a record. It has some value. I don't really care too much at the moment. Say I insert 3 into my tree here. Okay, so that's what I said to do over here. You place it on the deepest level, so you just work your way down. Think of this in a level order fashion. In fact, you can literally read this just like that, literally. Like I said, 5, 6, 8. That's how it appears here. So if it makes it easier to remember how you can index into these, draw out the tree, and then you could read it level by level. That's the neat property of how we index into this array. So 3 would be sitting over here. So I would have 3. So 3 is right here. So remember, I know how big the array is going to need to be. So we're not going to worry too much about that at this stage. So I have 3. It's right here on position 13. And what I need to do is, well, look at it. Look at it. Okay. So is this a heap? Remember, the heap has to satisfy 2 properties. The heap order property and it has to have the shape. Now, it has the shape, right? It has that complete binary tree shape. However, the problem now is that we're not maintaining which property? The heap order property, right? 3 is definitely less than 11. And remember, we have it smallest to biggest. You want to imagine it like that. So what do we need to do? Now, this is where it gets really neat. What I want you to do is imagine this node sitting here like as if it was sitting in a bathtub. And imagine heavier things should sink to the bottom, assuming they are full of air or something. But really heavy things sink to the bottom. However, the things that are really light should float up to the top. So we're going to have a notion called bubbling up, meaning that we're going to perform a swap, and it's going to move up like if it was floating in water. So what we're going to do is so let me just finish up what I'm going to say, and then I'll show you how you do it. It's really simple. We need to maintain the heap order property. The heap order property. So we will bubble up. So bubble in the sense that you do a comparison. We're going to bubble up. We're going to bubble up the new element until satisfied. So this is really where it gets really neat. So remember, the heap order property just requires that this node is not going to be, so this node is not allowed to be, so I'm getting a little excited about this because it's such a neat operation. So you have the node, its children must be either the same value as it or bigger, right? So what I'm going to do is I'm going to take and look at each one of these versus its parent. If the heap order property is not satisfied among its children, then I'm going to swap them. So let me just walk you through this. So 3 versus 11. So remember, I know how to locate the parent. I told you how to do it last day. You just take the position. So notice I have 13. I'm going to -1. Then I'm going to divide it by 2. Well, after that, that's position 6. So what I would do is I would compare 3 versus 11. And I say, okay, well, is this going to maintain the heap order property? Well, look, this is bigger than that. So the answer is no. So what I'm going to do is I'm going to perform a swap. So I'm going to swap the contents of these two like this. So I'm bubbling up. I do a key comparison and then I switch them if they in fact it's in violation of this property. Are we done yet? Well, 8 is bigger than 3, so the answer is of course no. So what I'm going to do is I'm going to exchange the contents of these nodes, or their elements. Now, not to be confused with the elements I'm referring to as in our key value pairs. I'm referring to the positions, the contents, so that's why I'm referring to them as nodes, by the way. It makes it a little easier to talk about. So 3 and 8 need to be swapped because I compared 3 versus 8, and 8 is definitely bigger than 3, so we need to bubble up some more. How about 5 and 3? Well, we know that at this node here, the children are indeed bigger than this one. However, its parent is still bigger, right? Which violates our property. So all I do is I bubble up one more time. So now when I say bubble up, I mean we're doing one step of this bubble up process. So I'm going to do a swap. And now look, I'm at the root. I have no parent. So there's nothing that's going to be smaller than this or bigger than it beyond this root, right? So that means if I look at its children, since this one, now I'm going to explain the correctness of this. Okay, so this originally was the root. And we knew at that time that its children were either the value of the root or bigger. But however, if I swap these, you'll notice that now this had to have either been smaller or equal to 5. Thus, we're still maintaining the invariant that the heap order property is in place. So I already see that. So so I wasn't showing you it with the array, but I'll just keep it like this. Now, remember, the array does get updated as you're going along. In the notes, I show you how it does change each step. But this would be what the heap would look like when we're done. So just ignore array A here. We're going to reuse this heap again. That's why I haven't changed it. But in the algorithm, these elements would be being permuted in the array A. Okay? So this is how you perform an insertion. It's really not that bad. So all you do is you just look at your parent and say, hey, look, is your key bigger than mine? Well, if the parent's key is bigger, that means I need to swap them, right? We keep doing this. So I'll leave you to look at the notes for the pseudocode. Let's talk about the time complexity. So let's talk about the analysis for this case, because you're going to find that the analysis is going to be pretty much analogous across all of these main ones we're going to talk about here. So the worst case analysis here. So what's the worst case? Well, imagine that the node I'm going to put in, its key is less than every other node along its ancestors. So if I put this in, you'll notice that every single one of its ancestors, its key was bigger than it. That's our worst case scenario. In the worst case scenario, the element's key is less than every key of its ancestor. Of its ancestors. Remember, ancestors, it's a plural. So how long does it take me to insert inserting the element into the heap? How long does that take me? Now, assuming that the array is of the sufficient length, it should take constant time, because I know exactly where it should go. Where is this position every single time? Where is it? What position is this? If I have length 13 here, this is n minus 1, right? So I know exactly where it is. So I can actually do this insertion into my array in constant time, assuming the array is of sufficient length. So inserting the element takes constant time. Now, it's worth noting that you would modify the algorithm I've given you if, say, this became full, you would resize the array by potentially doubling it. Like I said earlier in this course, I'm going to justify at some point why doubling the array or using some multiplicative factor of the length of the array is a good choice for resizing the array. So remember, we're making the assumption that we know the array is of the sufficient size we need. However, notice, remember, every single time the last position is sitting right. So this is going to be literally where it's going to be located. Okay? So it takes constant time to locate that spot. Then each comparison. Now this is assuming that the comparisons for between each the keys takes constant time. This is an assumption I'm making. Then each comparison takes constant time. Between it and its ancestors. So how many comparisons do I have to do though? What's the height of this? This is big O of log n. So how many possible ancestors are there? Big O of log n. The height of the heap is big O of log n. Thus, big O of log n ancestors are compared. And insert takes big O of log n time. So insert takes logarithmic time. Isn't that neat? So it's a very simple algorithm. You just look at the parent and you just perform the swap if the key doesn't quite meet the heap order property yet. Okay? So insertion, really not that bad. So the whole idea is you're going to imagine so remember, just think of the idea of you putting in the element and you imagine it freely floating or sinking. In this case, it's always going to float. If it needs to go anywhere, it's going to float or stay in the same spot. Okay, so let's talk about removeMin. Now, I should be very, very particular here. How would you compute min? Well, min's going to be sitting in the root, right? So it's really easy to find. How about removeMin? Okay, what about removeMin? Okay, remember, removeMin, we need to remove the root. We need to remove that element from the root. So let me just to be clear, let me reset our heap again. I think that 11 here. Pretty sure we have 5, 8, and 11 here. Okay, so I'm just resetting the heap so we can talk a little bit about this. Okay. So what I gotta do is I need to remove this key, because that's the minimum right there. So I have to remove this. And then what I need to do is I have to do something, right? So let's first describe this. By the way, what's the root in the array? A sub 0, right? So simply remove element KB from A sub 0, which upon completion you'll return, which will be returned. So I'm going to return, which will be returned. So that's what we're going to do eventually. Then, okay, now this is where the whole trick is going to come down. This is really kind of neat as well. I really find heaps very fascinating because it's such a simple structure. So remember, in the algorithm I said, okay, you're going to get rid of, so, okay, 5 is gone. So 5 is going to go out, and here's 5. I have 5. 5 is being hung out over here. I'm hanging 5 out to dry. So I now have to fix the heap, because now look, hey look, there's nothing there anymore. We need to put something there. So what am I going to do? Now I want to maintain that shape of the heap. So all I'm going to do is I'm just going to take 13. Let's take 13. We're going to put it up here. So I'm going to take its contents down here, put it in there. So all I've done is I've moved this element into the root. But now we have a bit of a problem. Do you see it now? Then copy. Remember, we know what a sub n minus 1 into a sub 0. Of course, decrement n. Make sure you decrement n at some point. So now 13 is sitting up in the root. What do we need to do? Do we bubble up or bubble down? So in bubbling up, I had one clear contender I would always swap with, right? I always had the parent I would look at. What do I have to do now? I have to be a bit more careful here, right? Let's take a look at this. Okay, if I have 13, and I most definitely need to let it sink, right? 13 definitely needs to sink, but I don't know where it should sink. So do you see anything that's interesting here that I can maybe take advantage of? Do you see it? So what I need to do is I need to look at my keys here, the left and the right child. Would you agree with me that I would probably want to put the smallest possible key of my children maybe up in the root? Do you see that? So what I would need to do is I need to consider myself, and then I would consider my children. And if I have 2 children, maybe I should consider the one with the smallest key, right? So if I have 2 children, that maybe might be a good idea. So I'm just going to say we may need to bubble down. So I put more details in the written notes, like the pseudocode as well. We may need to bubble down to maintain the heap order property, right? But we don't really have a clear contender of which way it should go down the heap. Because remember, we need to still maintain the shape. But remember, I just need to find a place to put that 13. Remember, I'm not adding anything anymore. I've removed this and I've put that up here. So now I have to work within the structure itself to perform the swaps. So let me consider the first obvious case is if it's a leaf. So if the root is in fact a leaf, I'm phrasing this in a very particular way intentionally. If we are considering a leaf, we are done, right? Now, obviously, if I try removing from this and there's nothing there, I just return null, right? I'm not even going to write that down. That seems kind of obvious. So, we are done. So, if this was just this node here, there's nothing else to do, right? However, I'm going to mention that we are done such a subtree. Remember, I didn't really explain. You'll see why I say subtree in a moment. Such a subtree must be a heap. if there is more than one element, begin at the root. Root P, we consider it. And some child of P called C. So I'm just going to call that C. Now it's going to be two possibilities. There's either going to be that they have two children and they're going to do exactly what I said. You're always going to pick the one with the smallest value, right? If I always pick the one with the smallest value, do you see why I would pick that? If I pick the smaller of these two, for example, I can guarantee, because this one had to have been smaller than this one, and it's the smallest among its children, it must maintain the heap order property, right? So, if P has no right child, because that's a very real possibility. Remember, there's usually a left and a right child. However, there's possibilities where you're either going to hit a leaf, or which you're done, or you're going to end up having a left child and a right child, or just have a left child, because there's a bias in this tree away from trying to have right children, right? There's sort of a bias here. If he has no right child, then C is the left child. Then C is the left child. Left child of P. I should be a bit more specific. If P has both children, then C is the child of P, with smallest key. So you're just going to look at your children, you pick the one with the smallest key, the higher priority one. Imagine like you have two kids, and say you have a smaller kid that maybe is in diapers, and you have like a 12-year-old. The 12-year-old is probably going to be fine for the most part, but if you have a baby, that baby's probably going to have a diaper on, and that diaper might just be an absolute wreck. So if you have to look at your two children, you might want to spend time with your smaller little baby one in case the diaper is completely full. Yeah, don't look too much into it. Let's just say don't imagine explosive diarrhea, okay? So I'm going to consider these two possibilities. Then what we're going to do is if the key of P is at most the key of C, then we are done, right? Because remember, I compared it against both my children, and both my children were bigger by definition. Because if I consider the smaller of these two, or just the only one I have, and this is going to be, if this was bigger or equal to me, my key's value, then I would be done, right? Because the heap order property must be in play. Otherwise, that's supposed to be a semicolon, by the way. I'm sort of running out of space here. Otherwise, swap the contents of C and P. Swap the contents of C and P. Sort of running out of space here. And repeat the process. Repeat the process with C as if it were P. So all you're going to do is just repeat this process, okay? So let's look at this and let's apply this idea here. So I have two children. Which one is the smaller one? Because I have both of them. It's 6, like I have established. So I'm going to bubble down. So I'm going to use this bubble down procedure. I'm going to perform a swap between 13 and 6. So 6 goes up here, 13 is here. Now, I have two children still, right? Okay, I have 7 and 10. Okay, it's indeed bigger than both my kids. So I have 2 of them, so I just pick the smaller of them, right? I pick the smaller of the 2. So what do I need to do? I need to swap 7 and 13. So 13 goes here, 7 goes here. I continue the bubbling down, the little bit of bubbling. What I do is then what do? Look at it. 13, if I look at my two children, so remember what you would do is you would pick out what C is, and then you compare its key against your current one, P. So this is P right now. And now I look at my children, I pick the smaller of the 2, 14. 14 is indeed bigger than 13, or it's equal to 13. In this case, it's bigger. So we're done. And we're happy, right? So we got ourselves this process. So now, this is the great part. So then you would just return 5 at the end of this process. So you would perform the removal, then you perform this bubble down procedure. How long does this take? How long does this take? Well, it's quite similar, right? All I did is I did a little bit of surgery, right? I pulled this out, so I kept track of it. I just kind of kept it in a little box, kept it away. Just imagine me just like some sort of like hermit creature just hiding in the corner here. Just hiding away with the 5 over there. And then I'll give you back the 5 when you're done maintaining the heap. Yeah, don't put that into your dreams, okay? So the point is that I return this when I'm done this process, okay? So how long does this take? Well, this surgery here I did, that goes in here. That takes constant time. Then I do comparisons. How many comparisons can I possibly do? Well, it's proportional to the height of the tree, right? Because I have to compare it against possibly the deepest node. So how long does removeMin take? This has to take big O of log n, right? Because the height of the heap is big O of log n. Isn't that nice? So let me summarize what our results are. So I should mention the pseudocode for this is in the notes. And also the bubble down procedure. So, with a heap, we get the following results. We get the following results. So we have our method. So this is just the contrast with the other. So I have my method, then I'll have the running time. So min is empty and size. Okay, how long should each of these take? Remember, the min is just literally just at the top of the heap, right? So how can I access that so I can return it? Well, it takes constant time. This takes constant time, that takes constant time. This all takes constant time. How about insert? Remember, we said insert takes big O of log n. And removeMin takes big O of log n. That's much better if you look at it. And it only requires this cute array construction, which is very nice. So it's worth noting that I've stated that these take big O of log n. But however, this is under the assumption I know that what the length of the array is, which is very often being the case. However, as I'm going to mention either today or next class, these are actually based on amortized bounds, which I'll talk more about what amortized means when we get there. So when you have to resize the array, however, this actually can be in fact be linear, but that's not very interesting to talk about because normally when we talk about heaps, we normally know the size, or we know a way of doing it such that it's really what matters is this core operation. Okay? That's why I'm making that assumption. But I should make a note here that these results actually hold when you literally implement it as a literal tree structure, using like a linked tree structure. As a remark. So as far as we're concerned, we'll assume always, unless otherwise stated, that the array is of a sufficient size. However, you just need to keep that in mind. So if you're doing insertions, you might need to resize the array. If you do removals, you might need to decrease the size or shrink the array. But that's more of an implementation specific issue. However, we're making the assumption we already know how big the heap should be. If one implements the binary heap using a linked tree structure, which we talked about, our assumption about the array size is eliminated. So it takes a little bit more work to do this, but you can get rid of this assumption that I have. So these will literally be true running times if you make it into a linked tree structure. Okay? So I'll talk more about that difference involving the arrays actually when we talk about amortization in a bit. Now, I want to talk a little bit more about heaps. We're going to talk about a couple of things you can do with heaps. They'll fall in line with the kind of assumptions I've been making. The first one I want to consider is the concept of building a heap. So imagine because oftentimes you remember we have already an array-based implementation, and I told you, okay, well, when we know the length of the array, we get all these nice results. So what if I gave you an array and I asked you, okay, can you build a heap out of this? So the first question I'm going to ask is, how can we make a heap? Well, if I give you an array, you can naturally scan from left to right through it, and you can perform insertions onto a heap where you know the length of the array already, which is already the length of the original array, right? I can perform n insertions like this, right? That's how I can build one. However, how long does that take? How long does that take if I just did that? Well, each one of our insert operations is big O of log n, and I do n of those. So that means that it's going to take big O of what? N log n. So what I'm going to do is I'm going to show you actually how you can do it in linear time. So how you can do this process where I give you an array, make me a heap out of it. I'm going to show you how you can do that in linear time. So I'm going to say there is a big O of n time way to build a heap. And I'll use quotation marks here. You'll see what I mean in a moment. Bottom up. Then given or upon building an array of length n, perform Heapify. So Heapify is a method I'm going to give you. Now I'm going to show you how an actual example of doing this. And you'll see why I kind of phrase things in a way that's rather strange at first. So Heapify is actually quite simple. So I'm going to write down Heapify. So algorithm called Heapify. Now, the variant I'm going to give you has no parameters. However, many people will give it one parameter, which is just the input array, okay? I'm just going to assume that we already have array A accessible to us. So I'm just going to say none A with length n is assumed to exist in the priority queue. Now, if you don't want to make this assumption, you just put the array as the input, or you could just assume it's some other structure that is using the input array A. The key point is that you have access to the array. So I'm going to say results in A being a heap. So I give you some array A, and what it's going to do is it's going to turn it into a heap, into a min-heap. So I'm going to start off with a starting index. Now this is going to look really arbitrary at first. Then when I do the example, it's going to look a little bit more sensible. So what I'm going to do is I'm going to start off with a start index being the parent. For the parent of the last element will be located. So this is the location, by the way. Remember we just said that, okay, if I give you some location in the array, how do I get its parent? Well, I take that index, minus 1 divided by 2, and I round it down, right? That's the start index. Remember, that's just the parent. So I'm going to start off there. And I'm going to, while the start index is greater than or equal to 0, you're going to do the following. So you're going to perform the bubble down procedure. So remember, bubble down, this is going to be, so in our removeMin operation, we took out that one element. Remember, we gave it to the hermit in the corner? And then what we did was we then did this bubble down procedure after we copied the last element into the root. Then we had this bubble down. That's what I'm referring to. That's what bubble down is. It's these key comparisons where I pick the child with the smallest value or the left child if there's no right child, okay? So that's what this process is. That's what bubble down is. So it has two parameters. This is the index for which you're going to be bubbling down from. In removeMin, it's 0. And then n-1 is the end index. So you're never going to go beyond this location. So you'll just pretend that anything beyond that number just doesn't exist in the heap. It becomes useful in the application we're going to talk about after. Then I'm just going to decrement the start index by 1. And that's it. Really straightforward. So let me draw out a heap, and I'll show you how this works. It will make a lot more sense as soon as you see the heap. I must remind you that the pseudocode for all those, for like bubble down, that's in the notes. But you already know what bubble down does. So I'm going to do a smaller example here. So I'm going to have an array. Imagine I give you an array with 6 elements in it. That's 8, 2, 7, 3, 4, and 1 in it. Okay, so this is my array that I'm being given. And my job is to turn this into a heap. So remember, this actually has a representation. Now, just to make it a little easier to visualize, I'm just going to imagine there's like these phantom nodes that I don't really know what they do quite yet. However, the great thing is that if you look at how this works level by level, you know, 8, 2, 7, so you'd imagine 8, 2, and 7 here. What's in the bottom level? 3, 4, and 1, and then there's going to be nothing in the last spot, right? So I have 3, 4, 1, and then there's nothing here, right? So nothing is here, right? So just keep that in mind. So if it makes it a little easier, you can always just imagine there's just this fake one just sitting over here, but there's nothing there, okay? So you can imagine that we've already considered these ones here. These are all interesting. If you look at each one of these separately, what are they? What is the subtree rooted at 3? Is this a heap? Yeah, it is a heap, right? So what I want you to do is imagine this as a heap. So this is a heap with one element in it. This is also a heap with one element in it. And this is a heap with one element in it. So what I'm going to do is I'm going to now consider something interesting here. So what I'm going to do is I'm going to have my start index. Remember, that's the parent of the last element. That's, okay, what's the parent of 1, 2, 3, 4, 5. Oh, for some reason I put a 6 here. That's strange. Anyways, the parent of 1 is which one? Well, it's 5 minus 1 divided by 2, which is it's 2, right? So it's 7. So 7 would be right here. But what do? I perform bubble down on that start index. So I do bubble down from here to here, right? So what is this though? 7's right here. So imagine 7 right there. Is this, so I want you to look at this like I'm building a smaller heap. So I want to imagine this like a heap. To maintain the heap order property, what do I need to do? I would need to bubble down 7, right? But I have no right child, so I'll pick this as the child. And its key is, in fact, less than this one. So it means I have to swap them, right? Now, I don't have enough arms here. So 7 goes down here. 1's here. And there we go. So you would agree with me that this is a min-heap, right? That's a min-heap right there. So far we've considered all the elements up to here so far. Okay, so then I decrement start index, so now I'm considering right here. Then I do bubble down. Okay, so now you got to imagine 2's right here. And what I want to do is I want to build another heap rooted at this node. What do I need to do? Do I have to do anything? No, of course I don't. It's smaller than its children. So that means that I have these nodes like this, and thus I have another heap rooted at 2. So this is what I mean by the bottom-up approach here. So notice I'm building it bottom-up by starting at the leaves, and I work my way up so that I build an entire heap. So far I've considered up to 2. Okay, the last element here, that is position 0. So I do this iteration, because it's equal to 0 now. I do bubble down from 8. So I have 8 right here. What do I need to do? Well, 8 is most definitely bigger than both of these. Which one should I take? Which one should I take? 1, right? It has 2 children. I pick the smaller one with the smaller key. I perform a swap. 1, 8. And okay, is 8 bigger than, I don't have any child here, so I have to perform a swap between 7 and 8, because 7 is in fact less than 8. And there we go. believe it or not, look at this. Now we have an entire heap. Now we have a min heap. So in corresponding positions, what should the array look like? What should it look like? It has 1 here. Its left child is 2. Right child is 7, right? Left child is 7. Okay, then we have 3, 4, and what should this last one be? 8. And there we go. That's what Heapify will do. It will take your array and it will convert it into a heap. But it doesn't bottom up like this. Okay? So, anyways, we're going to stop right here, and then when we come back, we're going to do the analysis for Heapify. I'm going to show you it takes linear time, and then I'm going to show you an application of sorting, and then depending on how much time we have after that, we'll talk about amortized analysis. Okay? So thank you very much, and have yourself a beautiful day.